All right, so this is a review for your Unit 4 test. The first topic I'm going to start with are these rates of change in particle motion. So I gave you guys a few different problems. First three were just kind of general rates of change. The one that's labeled 14, it says that a temperature in degrees Celsius of an object is given by this. So temperature with respect to time is what that notation means. So it's 3/8 t squared minus 15t plus 180 gives us a restricted domain from 0 to 20. At what rate is the object cooling at t equals 10? And then it mentions that we want to use correct units. So at what rate, whenever you see that, they're asking about a slope, they're asking about a derivative. So at what rate is it cooling, meaning like what is the rate of change of that temperature? So we're going to take the derivative. 2 comes out front here, makes that a 6/8 or 3/4, and then it drops down to t. The derivative here would be 15. The derivative of this would be 0. And we are specifically interested in what it is at 10. And they kind of give us a little bit of a clue here because they say at what rate is it cooling, meaning we should be expecting to come up with a negative number here. So we've got, this ends up being, let's reduce that down to 15 halves, which is 7.5, and then minus 15. So 7.5 minus 15 is negative 7.5, which makes sense because they said that it was cooling. And it said give correct units. So the temperature was given in degrees Celsius, and then the time was given in minutes. So the rate of change, think like change in y over change in x would be change in temperature over change in time. And so your units would be temperature in the numerator, time in the denominator. So that is our first answer. Next question, number 21, says the position during a 5-second trip is given by this equation. That is given in centimeters. Find a time t at which the instantaneous velocity is equal to the average velocity for the entire trip. So instantaneous velocity, that's just the derivative of this. So the derivative of t squared is 2t minus the derivative of t is just 1, and then that's a 0. So that's a formula that represents the velocity, which is the instantaneous velocity. And then it says the average velocity for the entire trip. When you see an average of something, you should be thinking of a slope. So the slope would be like the change in position over change in time over that 5-second trip. So the position at 5 minus the position at 0, that gives you the change in position, and then over the change in time. So it's like a physics definition. Velocity is change in position over change in time, and that's the average velocity over that interval. So we can plug these values in here. So if we plug a 5 in, we've got 25 minus 5, which is 20, and then plus 10, which is 30, minus, and then if we plug in 0, we have 0 minus 0 plus 10. And this is over 5. So I get 20 over 5, which is 4. So this is in centimeters per second. So the average velocity is 4 centimeters per second. The question asked, is there a time when the instantaneous velocity is the same as the average velocity? So what we do is we set the formula for the instantaneous velocity equal to that value, and then it's just a very simple equation. So add 1 to both sides and divide by 2. And then we end up with 5 halves, and t is in seconds. So it's actually like exactly in the middle that it's equal to the average rate of change. That's just kind of a coincidence there, so don't decide to make a pattern out of that. It just so happens to be that way with this one. All right, next one of these rates of change problems was number 45 that I pulled from the book. It says demand for commodity generally decreases as the price is raised. Suppose the demand is given by this right here. So the demand is in barrels, and then P is the dollar price per barrel. So they're saying if the price goes up, then the demand goes down, right? It's a supply and a demand sort of situation. So find the demand when P is equal to 40. So we're going to start with that. So find the demand when P is equal to 40. So this would be 900 divided by 40. So these would cancel out. So this would reduce down to 45 over 2, which is 22.5. And it says that D was given in barrels. All right, so the demand is 22.5 barrels. Estimate the decrease in demand if P rises to 41. Okay, so we want to know the decrease in demand if P rises to 41 and the increase if P rises to 39. So they tell us to estimate. And this question is weird because we could just as easily plug in the 41, just as easily plug in the 39. But the way that they intend for us to do this is to kind of set up a tangent line and use a slope. Okay, so we're going to set up a tangent line. The slope would be the derivative of this. So we're going to do d prime of P. It'll help to think of this as 900 times P to the negative first. All right, so the derivative, that -1 comes out front, and the exponent drops down to a -2. So we want to know what the derivative is at 40. So -900 over 40 squared would be -900 over 1600, and we can cancel out those zeros. We get a -9/16. All right, so that is the derivative. That is how the demand is changing as time changes, and we're going to use that to set up a tangent line. So normally it'd be y minus y1, like just giving you this empty tangent line formula, but now y's will be d's, and x's will be p's. So the value, the point of tangency that we're using is 40. The actual value at 40 that we found up here was 22.5 barrels. And then m is the slope, which we just figured out was a -9/16. All right, so what we want to do with that is we then want to plug in the 41. All right, so this, actually it says estimate the decrease in demand. So if we plug in the 41, we're expecting to get a negative value, which makes sense because this is negative. So we've got d minus 22.5 equals -9/16, and we plug in 41 minus 40. So this ends up just being a 1. So to solve for d, I could take 9/16 and then add 22.5. So 9/16 is 0.5625. So I'm gonna just plug this into the calculator. This ends up being 21.9375. So the decrease, it decreased by 9/16 of a barrel. So we really didn't even need to do this part of it right here, because this is the rate of change. That tells you what the decrease is. It'll go down by 9/16 if P is $41, and then the increase is actually the exact same. If I were to plug a 39 in here, this would be a -1, which would make this change a positive 9/16. So it would have increased by that exact same amount, 9/16 of a barrel, which who knows what that is in practical application, but we're just going with the numbers here. If the price went down. So price goes down, slight increase in demand, price goes up, slight decrease in demand. So that's what we're looking at. So that's a few just like general rate of change problems. I also put a particle motion problem on here for you guys. So we've got a graph, and I'm gonna keep putting that up on the screen. So this problem is labeled number 5. So let me do a quick sketch of this. Segment right here, here. Okay, so that is a velocity graph with respect to time. So we've got a handful of different parts here. So part A says, during what intervals of time is the acceleration positive? So one thing to keep in mind is that acceleration is the derivative of velocity, and we want to know when that is positive. So derivatives are positive when the function is increasing. So if v prime is positive, that means that v is increasing. So keep that in mind. So one thing that's really important is that a positive acceleration does not mean that whatever you're talking about is speeding up. Positive acceleration means the velocity is increasing. It might be increasing in a negative direction, or it might be increasing in a positive direction, and that would change your answer. Because if a negative number increases, it actually gets closer to 0. But obviously if a positive number increases, it gets farther away from 0. So positive acceleration simply means the velocity is increasing. So we're looking for where this graph increases, happens from here to here. So it happens on the interval from 0 to 2. Not here, not here. Then it happens again here on the interval from 6 to 7. You can do interval notation, that's my preference, or you can do inequalities, it doesn't matter at all. Letter B, what is the acceleration at t equals 4? Okay, so the acceleration at t equals 4, meaning that is the derivative of velocity at 4. So 1, 2, 3, 4. That is what we're looking at this point right here. And we can just check the slope, right? From this point to this point, we are going down 2 units, to the right 2 units. So that's a slope of -1. So our slope is -1. It means we have negative acceleration. Negative acceleration does not necessarily mean that our particle is slowing down. Negative acceleration means our velocity is decreasing. So it might be negative and decreasing, or it might be positive and decreasing. So the follow-up question, is the particle speeding up or slowing down? So this one, it has a negative acceleration with a positive velocity. So the velocity is positive and decreasing, which means it's headed towards 0. So headed towards 0 means slowing down. And we are going to say that this is because velocity at t equals 4 is positive and decreasing. So something positive that's decreasing heads towards 0, and when velocity heads towards 0, that means it's slowing down. So make sure you're checking acceleration and velocity whenever you have to answer that question. When does the particle change direction? The particle changes direction whenever the velocity is equal to 0 and changes sign. All right, so that happens right here. The velocity switches from negative to positive, so that happens at t equals 1. Changes again here at 5. And then we don't know here if it's actually going to change, so we're just going to include the 1 and the 5 because we don't know what happens after this point, just like we don't know what happens before that point. And letter D, when is the particle moving down? So notice they say we're moving on the y-axis. So for the y-axis, we're either moving up or down. So moving down would mean that we have negative velocity. All right, so negative velocity is like whenever we're below the axis here. That means that it's moving in a negative direction. So that would be from 0 to 1. And then again right here from 5 to 7. Okay, so expect to answer a bunch of questions like that about position, velocity, acceleration. Next, we've got our related rates. So I didn't actually number those, but we can just assume that they're 1, 2, and 3. So first one, an observer stands 500 feet away from a launch pad to observe a rocket launch. So we've got 500 feet right here. Here's your observer. And then this is, that's what launch pads look like. To observe a rocket launch, the rocket blasts off and maintains velocity. So this, it's blasting off. It's got flames and stuff. So that's our rocket. It maintains a velocity of 800 feet per second. Assume the scenario can be modeled as a right triangle. So that's what we did. How fast is the angle of elevation from the observer to rocket changing when the rocket is 1,200 feet from the ground? So we've got this right here that we said assumes can make a right angle. That's the angle that we're talking about here. And then we can use just h for height at this point. So our given information, we always want to set that up. Our given information, they tell us that the rocket maintains a velocity of 800 feet per second. So that is how this value h is changing. So dh by dt is equal to 800 feet per second. The way that it's worded makes it sound like it's always that value. It says it maintains that velocity. Assume, let's see, how fast is the angle of elevation changing? So that's what we need. We want to know when theta is changing, specifically at the moment when the rocket is 1,200 feet from the ground. So specifically at this moment right here. So that's our given, our needed information. Finally, we've got the equation that ties it all together. Whenever we're talking about angles, it's going to be something trig related. So this is the opposite, the adjacent. That means tangent is our best bet here. So tangent of theta is h over 500. And so we can set this up, take the derivative of both sides, and then we are trying to figure out what d theta by dt is. All right, so take the derivative of both sides with respect to t. So the derivative of tangent is secant squared, that's the derivative component, multiplied by the correction factor, equals, and then remember this isn't actually a quotient, it's just 1/500th times h. So the derivative would be 1/500th, and the correction factor would be dh by dt. So we're trying to solve for this. So to get this by itself, we would divide both sides by secant squared. So stay with me here. This is the reciprocal of of cosine, reciprocal of cosine. What we can do is multiply both sides by cosine to get it over to the other side, cosine squared. So think of this as like 1 over cosine squared. I can multiply both sides by cosine squared. Okay, so if I know all that info, I will find d theta by dt. So I have 1 over 500, dh by dt is 800 feet per second. And then the cosine squared, here's what I need to figure out. Cosine is adjacent over hypotenuse, right? So I don't need to actually find the angle, I just need the cosine of that angle. So cosine is adjacent over hypotenuse. The adjacent is 500 over the hypotenuse. That's what we got to do a little side work for. At this moment, h is 1200. All right, so we're going to use 1200 for h, 500 for that distance, and then we can find the hypotenuse. So I'm just going to use c squared for this. So 1200 squared plus 500 squared is 1690000. That is c squared. And then I can take the square root of both sides. So this ends up being a nice, neat 1300. Fun fact, this is like a 5, 12, 13 triangle, which is another Pythagorean triple. It just got scaled by 100. So it's a 5, 12, 13 triangle. So this is 1300, which I can then square. So this, I've got a lot of things that end up, just kind of reducing and canceling out. So this, I can cancel out these hundreds. I can cancel out these hundreds. And then this one, I have 1/5 times 8 times, and then this ends up being 25 over 169. So this can reduce down. And then I have 40 over 169. And this is supposed to be how the angle is changing. And they give us the units, radians per second. All right, so that's our first related rates problem. Second one is a ladder example. So ladder problem, it says a 17-foot ladder is leaning against a wall. So here's our wall, here's our 17-foot ladder, there's the ground. We are able to label that 17, by the way, because it's constant. It's not that the length of the ladder would ever change as time changes. So it's moving and sliding towards the floor, The foot of the ladder is sliding away from the base of the wall at a rate of 4 feet per second. So we are just going to go x and y for these, just keep them nice and easy. So our given information, it says that the foot of the ladder is sliding away from the base of the wall. So that means the foot is sliding this way. That means that the measurement of x is growing. So that is dx by dt that they give us, and we know it's positive because it's going to be increasing. So it is 4 feet per second. How fast is the top of the ladder sliding down the wall? So we want to know how y is changing, and we're expecting it to come out to be negative. Because if the ladder is sliding down the wall, that means y is actually decreasing. So we're interested in that value when the top of the ladder is 15 feet from the ground. So that's this measurement right here would be 15. So at the moment when y is equal to 15. So that's our given, our needed. Our equation that ties it all together is Pythagorean theorem, which we use a lot of. So it's going to be x squared plus y squared equals, I get to use the 17 here because it's constant. It does not change as time changes. So I don't have to assign it a variable. I can just use that constant. So take the derivative of everything with respect to time. We've got the derivative rule here times the correction factor plus the derivative rule here times the correction factor equals, and then 17 squared is just a constant, so the derivative of that would be 0. Even if you assigned it a variable and took the derivative, the rate of change, the part that looks like this, would just be 0 because it's not changing. So either way, you should have a 0 on that right-hand side. All right, so let's plug in what we do know. So 2, we don't know x directly, but we have the information that we need to find it because y is 15 and we know that the latter is 17. So we can say x squared plus 15 squared is equal to 17 squared. So we have x squared plus 225 is equal to 289. Subtract from both sides, so I end up with another Pythagorean triple. So that is an 8, 15, 17. So x is 8, dx by dt is 4, plus 2y at that moment is 15, and then this dy by dt is what I'm trying to solve for. So I can subtract this. So 2 times 8 is 16, times 4 would be 64. So I can subtract 64 from both sides, and 2 times 15 is 30. So just divide both sides by 30. We'll reduce that down. So negative 64 over 30. I think it might just reduce down by 2, and that's it. Yeah, negative 32 over 15. Like we said earlier, we're expecting it to be negative, and this would be in feet per second. Situation like this, it might make more sense to have it as a decimal, just so that kind of makes sense to you. There's a 3 repeating there. So either way, decimal or fraction. With the repeating, you actually do make it an exact answer rather than approximation, so that's totally fine. All right, our third related rates problem here says water runs into a conical tank at the rate of 9 feet cubed per minute. So we've got our tank, and then that quantity that they told us, that's the rate of change of volume. You can tell based on the units. So it's 9 feet cubed per minute. The tank stands point down and has a height of 10 feet. So this is like the actual height from end to end if it went all the way up, if it was all the way filled. A base radius of 5 feet. So that means the top has a radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So the water level is going to be somewhere in here, and that part's all filled up. So we are interested in how fast the water level is rising. So let's call that an h. And then the radius at that moment, we'll make that just an r. All right, so we've got the volumes. This is our given information. And what we are interested in is how fast the water level is rising. So that's how h is changing. That's dh by dt at the moment when the water is 6 feet deep. So that's what we're interested in. Our equation is going to be the volume of a cone, like this. So the volume of a cone is pi over 3 times r squared times h. You don't need to use both of these variables. We saw something like this in the notes. This is a cone, which means no matter where the height is, it's always a similar triangle. All right, so set up the similar triangle. Initially, it's 5 to 10. And so we say that anywhere the height is, it's just r to h. So that means that the r is always half the height, because it's always like a 5 to 10 ratio, right? So we could say that 5 over 10 is always equal to r over h, which means that the radius is always half the height. So I can take that, I can sub it in here, and then I can make my volume equation all in terms of h, which is the way I want it anyway, because they ask me about a bunch of h stuff up here. So r squared is 1/2 h squared. Multiply that by h. So I get pi over 3. When I square this, I get 1/4. So my constant out front is a pi over 12. When I square this, I get h squared, and then I multiply it by 1 more h. So that's my volume formula. So much simpler when I only have one variable. So now take the derivative of both sides with respect to t. So the derivative of volume is just this, equals, and then this guy, I do my derivative rule. So the 3 comes out fronts, making this a pi over 4. Power drops down to 2, and then I multiply by my correction factor. So it looks like this. This is what I'm trying to solve for, and I have all the other information that I need. dv by dt is 9. And we have pi over 4. H at that moment we said was 6 squared times dH by dt. All right, so let's simplify this a little bit. So 6 squared is 36, and then I divide that by 4, which is just 9 times pi times dH by dt. And then if I divide both sides by 9 pi, the 9's will reduce, so it just ends up being a 1 over pi is my dH by dt. And you want to make sure you have units there too. That would be in feet per minute, because it's just the height. Height is just a one-dimensional unit, just feet. All right, so those are our related rates problems. On the next page, we've got some linearization stuff. Remember, linearization just means tangent line. So the first thing that we are doing is approximating 17 to the 1/4 using linearization. So that means that we are supposed to be setting up a tangent line like this. So the point of tangency, we want to come up with our function, and then we want to come up with the value that we can actually do without a calculator. So our function is just something to the 1/4. So something to the 1/4. Now we obviously don't know what 17 to the 1/4 is, but the closest we can get is 16. So we're going to use 16 as our x value, which is our point of tangency. So let's start to plug things in. So y minus something equals m times x minus 16. So 16 is our point of tangency. The y value is from plugging the x value into the function. So that would be 16 to the 1/4, which is 2. And then for the slope, you get the slope by plugging 16 into the derivative. So I also need my derivative. 1/4 comes out front, exponent drops down to a -3/4, and then I can plug the 16 in there. So -3/4, we do the 4th root first, which is 2. Cube that, which gives us 8, and then the negative means flip it. So that's 1/8 multiplied by 1/4, which would be 1 over 32. So that is my slope. All right, so now I have my linear function, my tangent line, and now I just plug the 17 in for x, and that gives me my approximation. So I can solve for y by adding the 2 to the other side, and then I plug my 17 in here. So this is just a 1, so this is just 1 over 32, so I can say 2 and 1 over 32. A nice little mixed fraction there, no need to do a decimal. So that's one way to do a linearization. We also have a couple book problems that I pulled. So like this one, we've got this parabola here. They give us a tangent line that is labeled. Point of tangency is 4, 2, and then the tangent line goes like this, gives us another point out here. And then they ask us to estimate f of 4.03. So we're doing exactly what we did up here. It just presents it in a different way. They give us different information. So we know that we're still going to be doing a tangent line. So the point of tangency here is 4, 2. So 2 is the y value, 4 is the x value. We know that. And then they give us the second point so we can figure out what this slope is. All right, so the slope is just like an algebra slope rather than a calculus slope, because they give us the 2 points that we can use to compute. So change in y would be 4 minus 2 over change in x, which would be 10 minus 4. So we end up with 2 over 6, which is 1/3, and that gets popped into this tangent line right here. So then they say estimate 4.03, that function. So just like we did up above with the 17, we can plug 4.03 in for x and then start simplifying. So to get y by itself, I'm going to add 2 to the other side. And this is just 0.03. So this, even though this is a decimal, I can still cancel these 3's. When I cancel this and I cancel this, that means the hundredths place is a 1. Right? So this just ends up being 0.01, so it's just 2.01. So that is my approximation. Oops, that's been off the screen. Sorry, I think just the answer was. All right, one more linearization problem mentions, for number 30, something about stopping distance, which is given by this function right here. And that is given in feet, where s is the speed in miles per hour. So we're supposed to use a linear approximation to estimate the change in stopping distance per additional mile per hour when s is 35 and when s is 55. So we don't actually need a full tangent line here. They're essentially just asking us for the slope at those points. So it says to estimate the change in stopping distance per additional mile. That is just the fanciest possible way that they can say slope. So we want the derivative at 35 and the derivative at 55. So we're going to find f prime just as a function first. Derivative of this would just be 1.1 plus, and then when the 2 comes out front here, think without the decimal, right? So if I took 54 and multiplied it by 2, I'd get 108. So if I take 0.054 and multiply that by 2, then I end up with 0.108, and that's just an s. So that's my slope. I specifically am interested in this slope at 35 and 55. So 1.1 plus 0.108 times 35. Now this is something that you would have your calculator for. So 1.1 times 0.108 times 35. So this is 4.158. Let's make a little bit of sense, include the units. F is given in feet per, and then this is given in, this is the speed in miles per hour. So feet per miles per hour. So that means, remember, s is the stopping distance. That means that if you increase the miles per hour by 1, it's going to take you this much longer to stop. That's the stopping distance, right? You put the foot on the brakes, how long does it actually take to stop? The faster you're going, the longer that distance would be, right? If you're going really slowly, you could slam on the brakes and stop in like a foot. So this increases. Then we want to know at 55, how much is it increasing? So same derivative, but this time we're plugging in the 55. And again, I'm just going right into the calculator. This is 6.534. So proportionally, the faster you're going, the quicker that stopping distance is going to grow. The stopping distance is always going to be growing itself, but it's actually growing at a faster rate that you can see from these things right here. It's not just constantly growing, it's consistently getting faster. All right, last topic that we've got is a few L'Hopital's examples. All right, so L'Hopital's rule, we've got 4 or 5 examples right here where we start by just showing that L'Hopital's actually applies, which means if we try to plug the limit in directly, we would get 0 over 0. So starting with this one, just kind of a run-of-the-mill rational expression. We try the direct substitution, so if we plug 3 in here, we get 12 minus 12. We plug 3 in here, we get 9 minus 15 plus 6. And that's a 0 over 0. So this is one example, I included this on purpose. This is one example where you could definitely factor and cancel, and you'd get the same results. But this is just showing you that even in a situation where you could factor and cancel, you could just take the derivative top and bottom, do L'Hopital's rule. So remember, this is not a quotient rule. You're just replacing top and bottom with their own derivatives. So the derivative of the numerator is 4 over, and then the derivative of the denominator, the derivative of x squared is 2x. The derivative of this is negative 5x. I'm sorry, just negative 5, and then the derivative of 6 would be 0. So now you can sub the 3 in again. If I sub the 3 in here, I get 6 minus 5, so this ends up being 4. So that's the value of the limit, and you would get the exact same thing if you were to just factor and cancel and then try to plug the 3 in again. Next one, 103. So this one is a little bit tricky because it doesn't actually look like a quotient, but I'm going to show you a little trick. So we have x to the 1/2 times the natural log of x. You need to force it into being a quotient. So what we're going to do is we're going to leave this in the numerator and then flip this to the denominator by saying it's this. Now you have a quotient. Now we can sub in that 0. So if I sub in a 0 here, natural log of 0, if you can picture this function, looks like this. The closer that we get to x equals 0, this just shoots down to negative infinity. And then x to the negative 1/2, that means you're putting the square root in the denominator and making that 0. So remember, if we have 0 in the denominator, we consider that to be one of the infinities, depending on which way you're coming. And it doesn't really matter which one. For our purposes, this just means this is going to be indeterminate. So we can set up L'Hopital's rule. So going with this version of it right here, we take derivatives. Derivative of the numerator, derivative natural log is 1 over x. And then the derivative of the denominator, x to the negative 1/2, where a negative 1/2 comes out front. Power drops down to a negative 3/2. And now let's manipulate this around a little bit. All right, so this, I'm going to take the negative 3/2 and pop it up to the numerator. Same thing here. This is a 1/2 in the denominator, so I could make it a negative 2 in the numerator. And I could take x to the 3/2 and put that in the numerator. And then this one, since I have a 1 over x, I could put an x in the denominator. So just rearranging that a little bit. And then one more move, I can reduce these down. All right, so this 3/2 as an exponent and then 1 as an exponent. Remember, you can subtract exponents and we get this. So now I can sub the 0 right in, and when I sub the 0 right in, I just get 0. Next one, more L'Hopital's rule. So this is the limit as theta approaches 0. It's going to require a little bit of chain rule action here with that nested function. And then a little product rule action with this one right here. So I plug the 0 in. 2 times the sine of 0, so the sine of 0 is 0, minus, and this is also the sine of 0, which is also 0. Here, sine of 0 is 0, minus, and this is 0 times 1, but still 0 here. So we get 0 over 0. That means we are able to use L'Hopital's rule. So I'm going to go through and replace top and bottom with their derivatives. So 2 times sine. The derivative of 2 times sine would be 2 times cosine. Minus, and then this requires a chain rule. So we do the derivative part first. Derivative of sine is cosine. Leave that nested function in place. And then you're going to multiply by the derivative of the nested function, which we call the correction factor. So the derivative of 2 times theta is just 2. Over. Now down here, the derivative of sine is cosine. Minus, and now this is a product rule. Remember, theta is just like an x. So we do the first function times the derivative of the second function. And this is a big product rule with subtraction out front, so we need to be careful with our signs. Derivative of cosine is a negative sine. And then plus the second function, which is cosine, times the derivative of the first function, which is just 1. So that is everything all in place here. Let's try the substitution again. So 2 times the cosine of 0. The cosine of 0 is 1. So that's just a 2. Minus, this is the cosine of 0 again. So cosine of 0 here is 1. We multiply that by 2. Over, and then down here, cosine of 0 is 1. Minus, when we sub all this in, this I end up with a 0 right here. And then plus the cosine of 0 is 1. So this, I unfortunately end up with a 0 over 0 again. So now we go through, because this is 0 over 0, that means I can use L'Hopital's on this guy. All right, so let me just rewrite this a little bit. See what I can do with it. So I'm not actually changing anything. I'm just rewriting it to make things go a little smoother. Over, so in this I have a cosine minus a cosine, which maybe if I had noticed that from the beginning, see that these guys will cancel. And then this is minus a negative, so this is just a positive theta times sine theta. So now I can go through and I have to do L'Hopital's rule again. So I'll double L'Hopital's rule. So top and bottom, replace each piece with its derivative. So the derivative here, 2 is just a constant multiple, and the derivative of cosine is negative sine. So it looks like this. Minus, again, 2 is just a constant multiple. The derivative of cosine is negative sine. We leave our 2 theta in place, and then because it's a chain rule, I need a correction factor, which should be 2. Over, and then down here I can do a product rule with the theta and the sine theta. So the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay, so let's start subbing things in again. So subbing in a 0, I have negative 2 times 0, which would be 0, plus, and then this sine of 0 is another 0, over, and then this guy right here, I get 0 times 1, which is 0, plus sine of 0, which is another 0. All right, I'm now having some regrets about this problem because I don't know if this is going to get any better. I wonder if I'm going to do this one more time, and then I might just put a pause on this one because I did not try these out before. So this is another 0 over 0. So I'm going to try this just one more time. We'll see what happens. All right, so derivative of this. The negative 2 is a constant. Derivative of sine is cosine. Plus, now this one has a 4 out front, so it's going to keep its 4. Derivative of sine is cosine. We leave the nested function in place, and then multiply by the correction factor, which is a 2, over, now this guy down here is going to be a product rule. So we have the first times the derivative of the second, plus the second times the derivative of the first. And then this guy, that's just the derivative of sine, which is cosine. Okay, so let's try one more time to plug that theta equals 0 in. So if I plug 0 in here, cosine of 0 is 1, so this is a negative 2. Plus, this is an 8 out front right here, and cosine of 0 is 1, so that's an 8. Oh, this is looking much more promising. This is a 0, so this whole thing is 0. Cosine of 0 is 1, plus cosine of 0 is 1. Yes. Okay, so we get 6 over 2, which is 3. Lots of wonderful, fun times. Multiple iterations of L'Hopital's rule, which, fun fact, you can do it repeatedly until you eventually get somewhere. So we've got 3. We will eventually get somewhere. If you keep getting indeterminate forms, if you start out with 0 over 0, that means there is a limit. You might just have to work really hard to find it. I was not prepared in advance for just how far we'd have to work to find it. All right, 107. The limit as t approaches infinity of the natural log of t plus 2 over log base 2 of t. So infinity, when we're looking at these natural log functions, they look like this, and they grow very, very slowly, but they both do eventually approach infinity. So this one just keeps going up, this one just keeps going up. So that's another version of the indeterminate form, is infinity over infinity. So I do L'Hopital's rule. I take the derivative, top and bottom. So the derivative of natural log of t over 2, that's a little chain rule. The derivative rule is 1 over t plus 2. And the derivative of the nested function is just a 1 over, and then this guy, remember the derivative of log base anything else, you do 1 over, you have natural log of that base, and then multiplied by the variable. So let's try that again. All right, so this ends up being 1 over this. So this guy, when we set this up, they are both fractions like this. So taking this and dividing it by this is actually the same as multiplying by just the natural log of 2 times t. So it ends up, we can kind of swap numerator and denominator like this. This would be like if you had like a 1/4 and divided it by a 1/2, you could put 2 over 4. So that's what we end up with here. So now let's try the infinity again. So this, we go through, we try the infinity again. This is just multiplying infinity by a constant, so that's still infinity. This is just adding infinity to 2, so that's still infinity. So we've got another one where we have to do multiples. So let me write this again. So now, I'm just going to copy down what I had again so it's on the screen. So this is what I had originally. I got another indeterminate form, so now I replace top and bottom with their derivatives. This is just a linear function, so the derivative there is just the natural log of 2. And then the derivative of t plus 2 is 1. So that actually is just a constant. There isn't even anywhere to plug anything in. So my limit is the natural log of 2. One more L'Hopital's rule here. So 109, we've got the limit as y approaches 0 of sine inverse. I gave you guys lots of different derivatives to practice here too. Minus y over y cubed. So we go to sub that 0 in. Sine inverse of 0, we'll talk about that in a second, minus 0, and then 0 cubed is obviously 0. So sine inverse of 0, sine inverse, instead of subbing in an angle and getting an answer back, you sub in an answer and you get an angle back. So this is saying like what angle has a sine of 0, and that would be 0. Or 2 pi, or negative pi, you've got a million different answers, but our sine inverse functions restrict you to a certain number of quadrants that you only give one answer. Sine inverse is restricted to the right side of the unit circle. So 0 is our only possible answer. So 0 minus 0 over 0. We know that L'Hopital's rule will work. So we do the limit, and then we replace with derivative. So sine inverse, practice that derivative from the last unit. We've got 1 over square root of 1 minus x squared. That's the derivative of sine inverse, minus the derivative of y, which is 1, over, and then down here we've got the derivative of y cubed, which is 3y squared. So we are already looking, we've got 0 in the denominator again here, so let's sub everything in. When I sub a 0 in here, this is a 0, which makes my denominator 1, so this whole thing ends up being 1 minus 1 over 0. So I get another 0 over 0. So this is going to be another one where I have multiple iterations of that chain rule. So this guy right here, I'm going to write this as 1 minus x squared to the negative 1/2 power. So this 1 minus x squared to the negative 1/2 power. So I can go through. When I take the derivative of this, it'll require a chain rule. So I can put the negative 1/2 out front. This stays on the inside. Power drops down to a negative 3/2, and then I multiply by the derivative of the inside, because I'm doing a chain rule, so this would be a negative 2x. And then 1 doesn't have a derivative. So in denominator, the derivative of 3y squared would be 6y. So I go to sub the 0 in again. So if this is 0, that makes this 1. So this whole thing ends up like this is then 1, because any power is still 1. That makes this a negative 1/2. But then I multiply by this, which I'm subbing in a 0. So my numerator is a 0. We know that my denominator is a 0. So I'm going to do it again. Let's clean up this numerator first, though. I have a negative 1/2 times a negative 2. So those will cancel out. And then I'm multiplying by x. So limit as y approaches 0. So for this numerator, I'm going to have to do a product rule. So I have the first function, which is this, multiplied by the derivative of the second, so that's just the derivative of x, which is 1, and then plus the second function, which is x, times the derivative of the first. So this is going to be a chain rule again. So the negative 3/2 comes out front. We leave our nested function right where it is. Power drops down to a negative 5/2, and then I do my correction factor, which is the derivative of this inside right here. All of that over the derivative of the denominator, which would just be a 6. So now I for sure know that my denominator is 6. So hopefully I get something nice and neat in the numerator. So when I sub in a 0, right here, 1 minus 0 is 0. Raised to any power is still 1. Multiplied by 1 would be 1. Plus, and then I sub in a 0 here. This is beautiful because this is all one big product. If I sub in a 0 here, I know this whole thing is just going to be 0. And then over 6 is a 1/6. So you will get there eventually. We've seen a couple now that we've had to do multiple times. So hopefully that's helpful as you guys review.